Hey there! Are you an A-level physics student who doesn't know which equation to use when an object is falling through air or vacuum, or if it's moving through smooth or rough planes? If you don't know, like our video, subscribe to our channel and watch this video till the end while we explain different cases. So, the core principle is the Work-Kinetic Energy Theorem. So basically this stems from the Newton's second law, and we know what that is. That is F is equal to ma, which is the resultant force equals to mass times by acceleration. So for example, we have a box, an object, any object that cannot roll, just it can slide, and let's say there is no friction. You are applying some force F, and this is the positive direction of the X, and you have actually moved X. This is the positive direction for displacement, and you have moved this object X displacement. So how do we find out the work done? So basically what we do is we rewrite this F, and sum of forces basically F. There is no other resistive force or no other force, so F times by mass times by acceleration. But we want to express acceleration in terms of the displacement, so we use 2as v squared minus u squared. So A would be 1 over 2s v squared minus u squared. So rewriting this would turn to be F equals to half 2s m v squared minus u squared. Now what if we multiply both sides by x, the displacement? So this becomes Fx equals to actually this should have been x over here. So x and x would cancel out on the right hand side. You would have half m v squared minus u squared. Notice that this thing is the work itself. The work done by force is equal to, and we are already familiar with what this is. This is a change in kinetic energy. Change in kinetic energy. We can simplify this by writing delta W equals to delta EK. So in the absence of any other force, any other resistive force, any other applied force, any change in height, strictly speaking, work results in change in kinetic energy. Now, this is the core principle of the Work-Kinetic Energy Theorem, but let's add complexity in this. Let's say we have a vertical motion also. Let's say we have vertical motion. So let's start with the general case first. So let's say you have an object, weight is downwards, the positive displacement is upwards, and we haven't decided whether it's moving upwards or downwards yet. We just need a simple general form of the equation first. So sum of forces equals to ma. The only force acting over here is mg equals to ma. However, depending on what the direction we have set, since this is opposite to the force, you have to remember that force this time it's negative because it's opposite to the displacement. So we are basically if we want to go in the positive displacement, in the positive direction, we are doing work against the force. So building on that, ma, the same as before, we multiply by the displacement on both sides. Let's call that s. We can do x also, doesn't really change anything. So the general form will turn into minus mgx equals to, and max we will do the same thing. This will turn into change in kinetic energy. So this thing, mgx, is your change in gravitational potential energy, and this thing is your change in kinetic energy. But what does this sign interpret over here? So let's first write it. Change in EP equals to change in kinetic energy. So delta EP equals to delta EK. But let's focus on what this sign represents. The sign has an important job over here. So for example, the case is object moving upwards. That means x is positive. The displacement is positive, basically. Displacement is positive. So what we would do simply over here, we will keep it as it is since x is positive. So we will just simply take the half m v squared minus u squared. We will take the minus sign on the other side and multiply it over the bracket. You will get mgx, and remember it's a positive. This is going to turn into half m u squared minus v squared. And another way the books usually write this is that the change in height is positive. So some books may also write it this way: half m u squared minus v squared. And just to make sure that the meaning is clear, the object is going upwards. So this is the direction of change in height. So if we designate this as height 1, this is your height 2, this would be mg h2 minus h1 equals to half m u squared minus v squared. So different forms of the same thing. However, what it means, this is representing gain in potential energy, and this, since you can see u, if the left side is positive, the right side is positive also. This would mean that u is greater than v, which would mean that the initial velocity is higher, meaning it's decelerating. So this is basically your gain in potential energy equals to loss in kinetic energy. What if this was going downwards? Object moving downwards. This time displacement is negative. So we don't have to do anything. So we had minus mgx, same formula that we had over here, minus mgx half m v squared minus u squared. This time the opposite is happening. So this is your, we can still say that this is your h, but this is negative this time, right? So what we would do simply is we just keep it as it is. We can keep it as it is, because when you have a negative displacement, this thing will already become negative. So this would be minus delta H, and this would remain as it is, v squared minus u squared. And the right side would basically just turn into delta H. And delta H is basically just the magnitude part. Half m v squared minus u squared. So basically this thing has turned into, since it is going downwards, it's going to be a loss in EP, that means gravitational potential energy, and gain in potential energy, kinetic energy. So remember what's happening over here, what was happening over here also, that this time the gain, there was a gain in potential energy and loss in kinetic energy. This time there is a loss in potential energy and gain in kinetic energy. But the general case, the general form, is basically this one. This is your general form. Depending on what we actually are trying to accomplish, you can reuse that, whichever one we want, depending on whether its displacement is positive or it's negative. Right, okay. So this was the case when there is no other forces. It's just gravitational force. So basically what's happening over here, that when the object was just falling in the absence of any resistive forces, total mechanical energy is conserved. So this would happen if the object is pulled by the gravitational force, meaning the weight basically. This would be the case when you have elastic force. It could also be the same thing if you have electrostatic force. The change in potential energy, not just gravitational potential energy, but the potential energy in general, see, these two also have potential energies. The change in potential energy would be equal to change in kinetic energy. So we dub these systems or forces conservative forces. But those forces which do not conserve mechanical energy, the non-conservative forces, where total mechanical energy is not conserved. Energy is not conserved. Usually we mean that the mechanical energy, which is the sum of potential and kinetic, is reducing, but this could also mean increasing also. So this could be due to any resistive forces such as friction, drag. This could be due to any applied forces also. That means accelerating forces, such as tension, which is lifting the body up and down, moving the body, anything. So we could be reducing the mechanical energy or increasing the mechanical energy also. Either way, those forces will be non-conservative. And that's where these two other forms will come. So let's see how that works. A simple case, an object moving through a rough plane. So you have an object like this. Same thing we did before, but there's a driving force over here, and you have a friction force, we'll call this Fr, backwards. And this is the positive displacement direction. So we would do the same thing. Sum of forces is equal to ma. Let's call this force P, for example. P minus Fr equals to ma. And A, again, we can write it as half S V squared minus U squared. We multiply the positive displacement from this point to this point, for example. You will have PS minus F, let's call it F, S equals to, on the other side the S and S will cancel, leaving us U with half M V squared minus U squared. So notice one thing over here, this part. So this is your work done by force P, and this negative one implies you are doing work against it. Work done against force F or friction. And this is your change in kinetic energy. So the minus sign over here, we basically use this same thing over here also, minus mgs. That had the same meaning. You are doing work against gravity. So work done against gravity is equal to change in kinetic energy. So work done against gravity, work done against gravity is your loss in Ek. But if you go it this way, work, since this time we are actually going towards gravity, displacement is in the direction of force. The work done by gravity equals to gain in Ek. Also, this is another way to write this. Otherwise, you can stick to the previous version. So, notice one thing, that the work done by force F is not directly turning into change in kinetic energy. There is the work done against F is causing a reduction from the net work done, from the work done by force P. So it's reducing the mechanical energy basically. So this is what you have to remember. So another way to write this is work done by P is equal to change in kinetic energy minus or plus, because the minus thing would go plus over here, work done against F. Now, let's take it in the vertical motion with air resistance. So, vertical motion with air resistance. Let's see how this works out. So, let's take a simple case over here. You have an object going downwards. mg is downwards. This time it's air, so the drag force will act upwards. We will consider this direction to be positive, so any displacement in this direction would be positive. So when we write sigma F equals to ma, Newton's second law, remember, we have to take negative mg. So negative mg plus d equals to ma. Remember, in the absence of drag force, A would have been minus G. But that is the reason. This is the reason why. So when we consider A to be v squared minus u squared over 2s as before, and multiply s on both sides, you will have minus mg s plus ds equals to ma, or m times by half m v squared minus u squared. Now this is the general form. Okay, so this is the general form. This is the this needs to be changed before we move forward. This is the first form. So what if the case is that it is moving upwards? This is the case. This is the moving downwards. Sorry, what we actually made, this is moving downwards. Because if it's moving downwards, the drag force is upwards. So this would be the case, basically. So notice one thing. The S is basically going negative. So displacement is negative. Displacement is negative. So let's call it minus delta H. So the change in height is negative. So when we do minus mg minus h, and this thing goes on the other side, half mv squared minus u squared, and this thing would be s. Remember, it's negative, so this would essentially turn into negative ds, and on the other side it's plus. So technically we could have left it over there, but remember, s is negative, displacement is negative, so this would have actually turned negative ds by itself. So what we actually end up with is mg delta h, or like mgs, whatever you want to call it, but the magnitude part of that equals to the change in kinetic energy and your ds. So basically what this all means is this is your loss in gravitational potential energy. This is your gain in potential energy, kinetic energy, and this represents the work lost or work done against drag. And this S is now, delta H. If you compensate for both sides now, this is now delta H. Because on the left side it was negative, just like the mg minus thing, and on the right hand side it becomes positive. Now what if it's going downwards? Upwards. So remember, if it's going upwards, the drag force would be acting this way. So both the forces are opposite to the displacement. I will leave it as an exercise over here. You can reach out in the comments to see how this works. Tell me, have you cracked it or not? Let's try with an applied force this time. Let's say you have an applied force let's say you have an object, the weight is downward, mg, but it is being lifted up by some tension force. For example, in an elevator, the acceleration is positive upwards. That means the body is accelerating. So body accelerating upwards. And this is the positive displacement direction also. So in this case, what will happen is sigma f equals to ma becomes t minus mg equals to ma. And once you multiply s on both sides, when you convert it into a work thing, this would become ts minus mgs equals to half m v squared minus u squared. Ts becomes half. So s, remember s is positive now. So s is positive delta h going upwards. So this becomes half m v squared minus u squared plus mgs. So what this represents is work done by tensile or tension equals to gain in kinetic energy plus gain in potential energy also. This is how it's working. What if it is moving upwards but with a constant velocity? What is going on then? So it's moving upwards. The tension is taking it upwards, but acceleration is 0, and this is still a positive direction. So actually we should have made it a little bit downward. So case is object lifted up with constant speed or velocity. So how would we crack this one? So same way as we did before, just one minor change. You will have t minus mg equals to m times by 0. So basically t is equal to mg. So this direction is positive. So this would become ts equals to mgs. Or a more easy way, th is equal to mgh. I'm using s just to show you the displacement, the difference between displacement and height. So this represents work done, and this is your change in potential energy. So at this time there is no change in kinetic energy. There is kinetic energy. We are not saying that there is no kinetic energy, but there is no change to it because it's moving with constant velocity. Just to summarize, you have change in potential energy plus work equals to change in kinetic energy. The sign, if this is this is increasing the total mechanical energy. If there's a change in potential energy also, if there is change in kinetic energy also, total mechanical energy would be increasing. Basically, yeah. So if it is less, that means negative. So the total mechanical energy would be decreasing. Total mechanical energy would be decreasing. Similarly, you have when this is 0, total mechanical energy conserved. And that's all you have to remember. The sign conventions obviously are important for change in potential and change in kinetic, but if you remember how to deal with these, you can do the work power energy topic from A-level math mechanics also and the physics mechanics also. Alright, so see you in the next video. Bye bye.